Here's a summary of the molecular representations we'll see for organic molecules. These are the two butane versions we saw. These are isomers because they have the same chemical formula, C4H10, but different structures, different structural formulas. So this is the straight chain version. You can see that from the line angle drawing. And when it's the straight chain, this is an N in the front, which stands for normal or N-butane. So that's the straight chain. When you have a branch off the main chain, that's an isomer. So the isomer is shown here in the line angle drawing. This is the branch off the main, the center carbon, and you add to the prefix iso for isobutane. These are the hexanes that we also look. So hexane has the C6H14 chemical formula. This is the straight chain version that looks like the zigzag line. But when you take the hexane and you form a ring structure, so that's called cyclohexane when you connect the two ends together. So this is now not the same chemical formula. There are two less hydrogens in the ring structure, so the formula is C6H12. This line angle drawing for cyclohexane is not a hexagon, so it's a quicker way to draw all of those carbons and hydrogens. Starting with a 6-carbon ring with 3 double bonds in it is called a benzene ring. We saw this before in the styrene monomer that forms polystyrene. So this represents 6 carbons and 3 double bonds. In the 6-carbon ring, these 3 double bonds have resonance, meaning they can move. So you can swap the position of the single bond for the double bond. So instead of these 3 double bond locations, they move to the next carbon over. The overall structure is a hybrid of both of those resonance structures, so it's drawn as a circle or it's drawn as a dashed line inside of the ring. This benzene ring we will see a lot in the medicines and drugs, which have more complicated structures, but it starts with this 6-carbon. This is the basis for medicines and drugs, and it's also the basis for a lot of aromatics. So aromatics, because of the nice smell, this is an example of an aromatic perfume. It actually says aromatics elixir on there, but it is not always pleasant smells. Aromatics also are organic compounds that are strong chemical smells, usually coming from paint and solvents. So this is the 6-carbon benzene ring with the 3 double bonds, and this is how it's usually shown with a circle in the middle instead of the 3 double bonds. So this is the molecular view, which is the closest to how this is in nature. And what this is it's a flat disk. So this is why many molecules includes aspirin, glucose, the sugar, and dopamine, which is a neurotransmitter. They all have the benzene ring as a starting point, a shape that's easy to add other structures or other atoms or build on this flat disk to start with. Here's a line angle drawing. When you see all single bonds, that means that these are all just carbons and hydrogens. Any other atoms have to be indicated by the element symbol, like putting an O for oxygen. But when it's just a zigzag line, it means that this is a bunch of carbons and hydrogens. The ends of the line are carbon, and then any angles are also carbon. So there's 1, 2, 3, 4, 5, 6 carbons in this molecule. This also represents hydrogens without showing any lines or any hydrogen atom symbols. This carbon here has 1 bond going this direction, so that means there must be 3 more hydrogens here. So that would be true on this end too. So there's going to be 3 plus 3 or 6 hydrogens on the ends. These carbons in the middle at these angles this carbon has 2 bonds coming out of it. So that means there's 2 more bonds going to hydrogens. So there would be 2 hydrogens here, 2 more here, and 2 more here, and 2 more here. So that would be 2, 4, 6, 8 hydrogens, plus the 3 plus 3, 6 there, for a total of 14 hydrogens. So that also could be calculated with the chemical formula for alkanes, which is CnH2n plus 2. So in this line angle drawing, there's the ends of the line, 1, 2, 3, so that's 3 carbons there. And then where these 3 lines intersect is another carbon. So there's 4 carbon atoms represented here. Now, this is not just a straight chain or just one zigzag line. This is a branch that's represented, so this is an isomer. And since it's 4 carbons, it would have been butane, but it's an isomer of butane or isobutane. So to determine how many hydrogen atoms, you look at each of these, which is, this is 1 carbon at the end, and 1 line, the bond to the center carbon. That means there's 3 hydrogens represented here, and 3 hydrogens would be here, and 3 hydrogens here. So that's 9. This carbon in the center, which already has 3 bonds bonding to those other 3 carbons. That means that 1 more bond leaves 1 more hydrogen, so that would be 3, 6, 9, plus 1 more hydrogen, or 10 hydrogen atoms. This is also calculated using the alkane chemical formula. When it's only carbon and hydrogens and all single bonds, it's CnH2n plus 2. So this is an example of a cyclic or a ring structure. So there's 1, 2, 3, 4, 5, 6 carbons on here. And determining the hydrogen atoms, well, you start with the fact that each angle is a carbon atom and there's 2 bonds coming out of it. That's every single one of those angles. So that means that there must also be 2 hydrogen atoms at each of these angles. So there's going to be a total of 12 hydrogen atoms on. So this is called cyclohexane. It's the ring version of hexane, the straight chain with 6 carbons. So this again is a hexagon, but there's also double bonds involved here. So there's still 6 carbons. There's 1, 2, 3, 4, 5, 6 points. So each of those represents a carbon at those angles. But how many hydrogen atoms are there? Well, at each point, at each angle, there's 3 bonds coming out of it. 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. So that means at each carbon, there's only room for 1 more, which is going to a hydrogen atom. So this would be 1, 2, 3, 4, 5, 6 hydrogen atoms. So the overall structure of this, which is called a benzene ring, ends up being a flat disk with all the carbons in a flat plane and the hydrogens extending out from the plane.